Okay, so on to model building, everyone, the exciting stuff moving forward. So what we need to do here is we're focusing on the best combination of variables to build our model, to predict our dependent variable, and we're looking at removing redundancy where necessary. In research, when we're doing regression analysis, it's done in all different ways. So every researcher will often have their own way of doing it. But what we're going to do is just teach you how to use one particular way, and you'll be able to build more complex models in the future if you just sort of have these basics at the beginning. So let's understand these. What we're looking at is the best combination of independent variables to predict our dependent variable, and we're going to use stepwise regression to do this, and in particular, backward stepwise regression. What does that mean? So that means that we start with all the independent variables in the model, and we're going to remove one variable at a time until we reach a model that we consider is the best model for our data. Please note this isn't the way it's always done, but this is a really good way to learn about regression, in my opinion. Okay, let's begin. So when we talk about the best model, what are we talking about? What we're talking about is the goodness of fit, and this can be assessed in quite a few ways. First, we look at the standard error of the estimate. So this is the error around that line of best fit, and we need to decide what's acceptable or not. Then we look at the coefficient of determination, the R-squared, the variance explained. And then we've got our adjusted R-squared, where our variance explained is adjusted for sample size and number of independent variables. So these are really important to look at when we're talking about our model. But going further into that, in terms of model diagnosis, I think these are some of the questions you really need to think about. So is the overall model significant? Are the independent variables significant? Is the amount of variance explained adequate? Is the standard deviation of the model, so the error, is this too large to provide meaningful results? Is there multicollinearity, and is this a problem? And have the assumptions for regression been met? So taken together, the goodness of fit and these questions, and there is overlap there clearly, you need to think about these things in terms of your model building. So here we go through some of the Excel output. We're going to start with the full model. When I say the full model, it means all independent variables go into the model. So to do this, let me show you. So we open that data analysis box yet again, and we click on regression. The first thing we need to do is look at our input Y range. So to do this, we select our dependent variable, which in my case is the first column of data. I always select the label because it makes reading the output a lot easier. Then we have the input X range, and we need to select all independent variables all together en bloc. And then I tick the labels box because I'm saying the first row includes the label. And then I like to tick the residuals, the standardized residuals, the residual plots, and the normal probability plots. So you can see that on the slide, and then I click OK. Okay, so here is the output for the full model. Please note this is not the final model, but I'm going to interpret this, and then I'm going to get to the final model, and then I'll interpret it again. And by doing that, hopefully, it'll all make sense. Okay, so firstly, starting with the standard error. So remember, this is in the unit of the data, of the dependent variable. So this is $1,530.44. Remember my car prices, my list prices for the cars are in tens of thousands of dollars. So my standard error is going to reflect that. If your data is in millions of dollars, your standard error is probably going to be a larger number again. Or if it's in very small units, then we'll see a standard error more closer to those values. So you need to consider your standard error and if it's acceptable by thinking about the range of your data for your dependent variable. Okay, so now let's look at the R-squared. So my R-squared is 0.528, which means I interpret as 52.8% of the variability in list price is explained by the variability in usage, seller type, colour, comments, photos, and transmission type. What this means is that 47.2% of the variability is unexplained. So again, you need to decide whether this is acceptable, and this will depend on how important the decision is going to be in terms of your model and so on. Okay, now the adjusted R-squared. So in my case, my adjusted R-squared is 0.469. And you know this is the R-squared and it's adjusted for the sample size and the number of independent variables. This is really useful for comparing models. So we will do this as we compare models. but for our final model we interpret the R squared. Okay, now we have the ANOVA output, and what this tells us is the overall model and whether it's significant. If it is significant, what this means is that at least one independent variable is significant in the model, or in other words, at least one independent variable significantly predicts the dependent variable of list price. In my case, it is significant, and you know that because if you look at your significance F, this is our p-value, and if this is less than alpha of 0.05, we reject HO, and we conclude that at least one variable is significant in the model. To determine which variable or variables are significant in the model, we need to look at the last part of the regression output. Here you can see the significance of the intercept and each of the independent variables in the red box that I've provided on the slide. Take a look at the p-values. As you can see, usage and colour are significant, but all other variables are not significant. The intercept is also significant. With backwards stepwise regression, we remove one variable at a time and then we rerun the model. We do this because a variable close to significance may become significant after the removal of another variable. Here, in my example, keep a close eye on seller type. Seller type has a p-value of 0.06, so it is not significant in this model, but may become significant when we remove redundancy from the model. If we were going to take all the non-significant variables out at once, we may in fact lose a lot of information and we may see a major reduction in the R squared. So I can hear you ask yourself or ask the computer, which variable do I remove first? Well, we remove the one with the highest p-value. In my case, we remove comments and then we rerun the model. Now, as we compare models, I want you to keep an eye on the R squared, adjusted R squared and standard error, because the best model, that's best in inverted commas, is the one that has the highest adjusted R squared, the lowest standard error, and all the independent variables are significant. Okay, so in this model, I have removed comments and then rerun the model. See, the change in the R squared and adjusted R squared is minimal, and this provides further confirmation that comments should be removed. In fact, the R squared hasn't changed at all, and the adjusted R squared has improved. In this model, usage, seller type, and colour are significant. Remember in the full model, colour was not significant, but now with the removal of comments, it is significant. This further demonstrates the importance of removing variables iteratively rather than all together in one go. Now in this model, photos and transmission are not significant, so we remove the one with the highest p-value, which is photos, which has a p-value of 0.70, and we rerun the model. Now in this model, with the removal of photos and comments, the change to R squared and adjusted R squared is minimal, and thus providing further confirmation that these variables should be removed. In this model, usage, seller type and colour are significant, but transmission is not significant, so we need to remove this and rerun the model. Okay, finally we have our final model where all independent variables are significant. Notice the R squared in the full model was 52.8%, and now in the final model is 52.3%. So there has not been much change there, and it shows that what we've done is remove redundancy from the model and kept the important variables. The adjusted R squared is the highest of all the models we considered, which is good, and the standard error is the lowest of all models considered. So here we have the best model, as it has the highest adjusted R squared, the lowest standard error, and all the independent variables are significant. Now, just because it's the best model, this does not mean that the model is actually useful. We need to decide if the standard error and the R squared are acceptable, for example. So now let's interpret our final model and decide if it's actually useful. The R squared is 0.523. This means that 52.3% of the variability in list price is explained by the variability in usage, seller type and colour. The standard error is $1,492.86. This is somewhat large but acceptable for the purpose of predicting list price, and the R squared is meaningful, it's over the 50%, and given what we're predicting, it's not going to be too problematic. Now here we have the beta coefficients. Let's interpret these. So the predicted BO value is 15,182 0.23. So this is our y-intercept. It's the value of y when all x values are 0. As this is outside the range of our data, it really is difficult to interpret, but what I often say to students is that it's a bit of a starting point for our prediction. Now B1, or the coefficient for usage, is negative 0.0387. This is interpreted as, for each additional 100 kilometres in a car's usage, the list price decreases on average by $3.87, holding constant all other variables. So that's how we normally interpret our numerical data. The other two variables are categorical or dummy variables, and so these need to be interpreted differently. The variables colour and transmission type are dummy variables, so we cannot interpret the coefficients in the same way as the numeric variables. If we did, we would be saying strange things like, for each additional colour, we expect the list price to increase by X or decrease by X. This does not make sense at all. Similarly, with transmission type, what would we be saying? For each additional transmission type, we expect the average price to increase, decrease, and so on. Doesn't make sense. So let's look at how we do interpret these. Instead, what we do is we interpret the coefficients as follows. For B2, which is seller type, we interpret this as, on average, if the seller type is private, then we expect the list price to be $917.55 less than when the seller is a car dealer, holding constant all other variables. For B3, the coefficient for colour, we interpret this as follows. If the advertised car is blue, then on average the list price is $1,056.03 higher than that of other coloured cars, holding constant all other variables. Note, in both occasions, the category allocated 1 with the dummy variable, i.e. private seller and blue, is the one that we interpret. That is why when we allocate 0 and 1 to our data, I've allocated 1 to the category of interest. Jane's car is blue and automatic, so this is why we want to understand these categories. We could, however, have interpreted the other category as this is just simply a change in the sign from positive to negative or negative to positive. But to keep things simple, I really think allocate 1 to your category of interest. Okay, so now we can produce the regression equation using the coefficients. I always think the equation is more user-friendly if we replace BO, B1, B2 with the actual variables and their labels. So in my case, the regression equation is shown on the slide. So predicted list price equals 15,182.23, subtract 0.039 times usage, subtract $917.55 times seller type, plus $1,056.03 times colour. On the next slide, I'm going to show you an example to understand this further. Okay, so here I have repeated the equation, and then I have included the data for Jane's car to answer the research question about what price Jane should list her car. Finally, I hear you say, okay, so by inputting Jane's car's features, such as 63,000 kilometres, private seller and blue, the list price is $12,864. We could set up a confidence interval, but essentially this is the prediction, acknowledging error and so on. Lastly, but perhaps most importantly, we need to check our assumptions for regression. Your book talks extensively about this, so let me just show you the doing side of this on my slides. First, let's check multicollinearity. As you would know from reading your book, this is when two variables are highly correlated with the dependent variable, which is great, but also highly correlated with each other, which is not so great. Regression works best when the independent variables are highly correlated with the dependent variable, but not highly correlated with each other. On the slide, the correlations between the independent variables and the dependent variable are contained in the red circle, and the correlations between independent variables are contained in the blue circle. When multicollinearity occurs, we may see all kinds of crazy things in our data. We may see counterintuitive results. We may have a high R-squared and overall a significant model, but then no independent variables are showing significance. We may see unexpected or incorrect signs in terms of the beta coefficients. We may see sizable changes in coefficients when we add or subtract different variables to the model. A variable that was previously significant may become non-significant when another variable is added, and so on and so on and so on. So there's a lot of weirdness that happens with multicollinearity. And so what I always advise students is please check your correlations first to get a feel for your data. And then when you perhaps see weird things happening in regression, you can understand what's going on. A quick way to do this, to check for multicollinearity, is to look at your correlations between between an independent variable with the dependent variable, and then that independent variable with other independent variables. And what we're expecting is the correlation between the independent variable and the dependent variable will be higher than the correlation between the independent variable with other independent variables. So it sounds a bit confusing, but have a read of my slide and I talk about the example of usage and go through those correlations to show how I check for multicollinearity. There is also a formal test that you can do. You can run VIFs, which are variance inflationary factors. Unfortunately, this software is not provided with your textbook. It is provided with other software packages. Excel doesn't do it. But so you can run them, but it is outside the course. You can just simply look at your correlation matrix, and this is sufficient. Okay, so to check other assumptions such as heteroscedasticity and also to check for independence of errors, we look at our residual plots. These show us what's left over after the model accounts for the data. These are produced through your regression output, and they were one of the boxes that I mentioned that you should tick when you're running your regression. So here you can see on the slide my residual plots. What we're seeing is a random pattern of the errors, and this is good. Residuals are about what's left over, so they're they're predicted, so what's left over. And what we can see here is just random error, so that's very good. So those assumptions are met. Another assumption, and I don't think your book talks about this, another assumption is normality. And the way we check for this is we can either look at our normal probability plot, and if it's a straight increasing line, then that's good, and the data is considered normal. Or what we can do is we can do a histogram and plot the standardized residuals and look for that bell-shaped normal distribution, and I've done that here as well. So here on my data set, you can see where I potentially have two outliers. So observation 25, where the list price and the predicted price, there's quite a difference there, and off at observation 36, we're also seeing that. And so you can see those outliers in the top of the histogram too, up the top here. And so look, they are looking a bit like outliers. And what I did to check this is I reran the regression with taking these outliers out, these observations out, and it really made little to no difference to the predictions, to the standard error, to the R-squared, so then I decided to keep them in. But it's always good to check these things. And look, it's not really really violating this assumption. The regression analysis is robust to this assumption to some extent, so you don't need to be too concerned unless you're seeing a real problem here. Okay, lastly, and perhaps this is more about me than about Doina, but I think it's really important when you write your report to avoid the use of technical language. So many reports that include stats are written quite badly, and some that are written well still use a whole lot of technical language, and they're really excluding a whole lot of people from understanding and reading their reports, because it's really turning them off because they just don't understand what's being written. And what I believe is that if you can present a very technical report in a very simple way, you really understand what you're talking about. So on the slide, I've put quite a few terms which no doubt you will need to discuss in your report, but perhaps you don't need to actually use these terms. For example, we know that correlations relate to relationships, and perhaps the word relationship could replace the word correlation. I always suggest to students that you should hand your written assignment to a non-statistical friend and get them to highlight any word that they don't understand, then rewrite this section. For example, multicollinearity. How many of you knew this word before the course? If not, throw it out and rewrite it using simpler terms. The simpler the better, as your report will have much greater reach if you do this. To end on a happy note, I wanted to tell you about a student group I had quite a while ago who wrote a report on the Fremantle Dockers. What they were looking at is predicting the score based on game stats, for example. And these students and their stats teachers had our 5 minutes of fame. We got the local paper picked us up and wrote an article on it, and the students did well in their assignment. But what was the most interesting thing is that the Fremantle Dockers thought the report was okay, but the West Coast Eagles loved the report. and they actually purchased the report from my students. So who says stats doesn't pay? On a serious note, I really hope this worked example has helped you understand more about regression and more about how to complete your business report. Good luck, everyone.